So what we have here is we have a great nice box fan here. These things put out a lot of air. They're great for cooling the house down. You can stick it up in the window. It's great, but this one here has gone dead. And when I turn it on, you'll probably hear it humming. Right? And we have no rotation on any of the speeds. Let's take it apart and see what's going on. Okay, we've got the back off of the fan now. So if I turn on the switch, you can see a little bit of rotation. The fan actually wants to try and rotate. If I spin it, it will continue to spin. If I can spin it fast enough, because we do have a power to the coil here. If I can spin this thing fast enough, it will continue to spin. It won't start on its own, and it won't spin very fast. But as you can see, it's going to continue to spin at this slow speed here. Okay, so this is a really crude illustration of how an AC induction motor operates. But basically you have two coils, and your AC waveform is applied across the coils. Now we need to create a rotating magnetic field. And how we do that on a single-phase motor, on a three-phase motor there would be three separate coils, one for each phase. On a single-phase motor we have two coils, and we need to create a 90-degree phase shift for the secondary coil. How we do that is with the use of a capacitor. And the size of the capacitor is selected based on the power and the rating of the motor. So sizing is important. If you go too big or too small, you could end up with a burned out coil. So in this diagram here, we'll see the schematic, basically how a run capacitor is used on a low torque AC motor. Now there are two types of designs of capacitor motor. One, this is a diagram of a run capacitor where the capacitor is always in the circuit, and what it does is it provides a phase lead or phase lag between the two coils that generates your phase shift for your rotating magnetic field to cause the motor to rotate. Higher power motors will typically use a larger capacitor and a larger starting winding, and a method to disconnect that capacitor once the motor is up to speed, such as a centrifugal switch that is essentially a weighted switch assembly mounted to the rotor, and once the rotor gets to a certain speed, the weights through a centrifugal force will spin out and open the switch and disconnect the capacitor, because on a higher power motor, once the motor is actually running at speed, you no longer need the capacitor in the circuit. Lower power motors typically will keep the capacitor always in the circuit just because it improves the power factor of the motor. And again, these are lower power motors, like such as a fan motor. I've had the capacitor blow on my compressor for my HVAC system a few times, and on those ones, they're pretty big capacitors, and they usually fail destructively and blow to pieces and have oil all over the place because they're oil filled. But the fan we're going to look at today just uses a small Mylar capacitor. I'm sure the capacitor is gone because the fan doesn't spin. But anyway, I just wanted to show you guys this is why a capacitor is used. It's used so that you create a phase shift between the two coils, so that you create a rotating magnetic field. Without a capacitor, it's not going to run. And if the capacitor were to short, which is another possibility, usually they don't short. Usually these capacitors are designed so that if they do short, they have internal fusing, so that if they were to short, it will pop that fuse. Because if the two coils were to become energized together, first of all, the motor wouldn't spin, but it would get hot pretty quick, and you'd end up with a burned out winding. So most of these capacitors are going to have some type of a fail-safe inside the capacitor, so that if the capacitor were to short, it's going to go open. So your normal failure is going to be an open capacitor. So let's go take a look at that. I bet it's going to be the capacitor that's gone. And we'll do some measurements and verify that we do indeed have an open capacitor. And that's due to, we have two coils, as I showed on the diagram. We've got our electrical energy going through the main coil, which is allowing the fan to spin because we've already started it, but our auxiliary coil is not energized, so we don't have our leading or lagging phase, basically. You need the two coils energized 90 degrees out of phase to create a rotating magnetic field. Right now we don't have a rotating magnetic field, but we've got the rotor spinning just due to the fact that I started it by hand. If I stop it, nothing will happen. And if I spin it the opposite way, it'll continue to spin the other direction too. Because again, it's a synchronous motor. It doesn't care what way it spins. It'll spin either direction when your secondary coil has no power. So here's our capacitor. We've got our switch here, and here's our capacitor. And this bad boy is going to be bad. So let's pull this bad boy out, we'll measure it, and we will see that the capacitor is going to be open. And then I'll find a new capacitor, and we'll put it in here, and that'll fix the problem. Guaranteed, that will fix the problem. So I'm just going to remove the capacitor, and we'll cut some of the tie downs, and then I can get my meter out and measure this thing. Okay, there's our capacitor. We'll just remove it. The capacitor is actually inside a case here, so I should be able to open this up and actually remove the capacitor. It's just in a white box here. So there's our capacitor. We remove the capacitor here. Now sometimes these things will swell up when they blow, but not always. The larger capacitors used on larger motors, the metal ones, typically they will blow. Like you'll know it because their capacitor is all swollen up and the case is damaged. So this is a 7 microfarad. It's an AC capacitor rated at 250 volts. So let's test this with my multimeter. So with a multimeter, we should be able to measure. Now this multimeter has capacitor features on it. If you've got a capacitance feature, use it. And this is a case where I'm going to use a capacitor meter. I'm testing for capacity. I'm not so concerned about ESR on this type of capacitor. It's not an electrolytic. This is a Mylar capacitor. Normally when you measure a good capacitor, we connect our probes up, and what will happen is that the ohms should drop very low initially, and then they should go high. But this one here, as you can see, my ohms is so it hasn't gone open, but it's actually built up resistance. If I put it in capacitor mode, I'm measuring like 0.6 microfarads. This is a 7 microfarad capacitor, and I'm measuring like 0.8. So this capacitor has gone open. That's what's happened on this one. So let's get a new one. Okay, I've got a new capacitor here. It's the same type as the original. It's a 7 microfarad, 250 volts AC. We'll hook this one up as well. I'm still in capacitor mode here on my capacitor tester. And we'll see that this one here is measuring 7.07 microfarads. Let's take a look at what this does when I measure it in the resistance mode. It should start out, it should dip down low momentarily, and then it should go infinite. It should go to overload here in a minute. As the capacitor charges up, our ohms will go up. And as you can see, as the capacitor charges, it resists more DC current flowing through it. And then my meter will go to its maximum range of 30 megohms here momentarily, and then it'll say overload. I think it's 32 is what this one goes up to. Well, made a liar out of me. $40 megohms. There we go. Went to 40 megohms and then went open, or went overload. This meter will measure up to 40 megohms. So that's how you can test a capacitor using a regular ohm meter. For the heck of it, let's just see what the ESR meter shows on this thing. So I've got my ESR meter. We'll zero it out, and we'll just measure with the ESR meter. There you go, 0.14. So it will pass. The ESR meter will pass it. For the hell of it, I'll just grab the other old capacitor and we'll measure that with the ESR meter as well. Okay, here's the old capacitor. It's open. Completely open. No good. Okay, let's get the new one. And we'll put it back in here and see what happens with the fan. It'll fix it. I'm guaranteeing that this will fix the problem, because there's really nothing else to go wrong other than a motor bearing, which we know isn't the case because it spins. So I'm going to just get my heat gun out here, and we'll get some heat shrink on it. We'll heat shrink that on there and put this thing back together. Now, polarity is not important because this is an AC capacitor, so it doesn't matter which wires I hook up. I'm going to solder the wires, and then I'm going to put the heat shrink tubing over it and heat shrink it in place before reattaching it. And I'll put some tie straps in there, zap straps, just to zap all the wires out of the way like they were originally, because I don't want them to get hit with the fan blade. So I'm just waiting for my iron to heat up here, and then we'll solder these wires and heat shrink them. Iron should be warm by now. Now we'll reattach the capacitor. What's nice is a lot of these capacitors, they actually have the mounting hole on them for mounting them, which is nice. Now there's a hole in here somewhere that this thing came out of. Okay, as you can see, got the wires zapped back into place. Let's turn on the power. There you go. 3 speeds. I needed that today. It is getting warm out here, so time to get your fans tuned up, and stay tuned. We'll do some more videos in the not too distant future. Got a few to do here. I'll give you a little preview of what's coming up. I have this. Ooh, a BGW Systems. 250 watts per channel. That's upcoming. We'll catch you in the next one. Bye.